I've just received another horrible looking problem from my Facebook feed, real juicy one to get stuck into. It's another shape problem. It looks like it comes from one of the long questions from the MAT Oxbridge entrance exams. And I mean, initially it looked quite straightforward, but then I started digging and discovered actually it was a bit of a bit of a beast, and it could also be a typical question from the top end difficult questions towards the end of the UKMT Senior Maths Challenge papers. Now, I've tackled it in two different ways. I've done it algebraically, which was quite brute force, and required some real sort of nasty algebraic, sort of heavy hitting. But then I found a really nice, elegant way of doing it, which I'll show you towards the end of the video, which wasn't immediately obvious. And then when I saw it, I was like, "Oh my word, that made things a lot easier." Okay, so I hope you enjoy it, and off we go.
Okay, so the way to deal with this problem is not to deal with the quadrilaterals we have inside, the blue, green, orange and pink ones, but to actually split things up into triangles. But first of all, we are told that the lengths here and here are the same, and here are the same, and here are the same. So basically the quadrilaterals are meeting at the midpoint. So this is kind of the key to unlock the problem. So first of all, I'm going to divide it up into triangles. I work better with triangles. Quadrilaterals are a bit problematic. And then I'm going to label my distances, or rather the base lengths of each of the triangles of x centimetres. We have no clue what that is at the moment. And I've also put in some dotted lines, which are vertical lines from this apex common to all the triangles. Okay, I'm actually going to label that P, Q. It's actually going to be a set of coordinates which we need to find out from some coordinate geometry. So what I'm now going to do is I'm going to set that to 0, 0, my origin. It's logical to start at point A. And at point C, because we have x plus x in the x direction and x plus x in the y direction, I've got my coordinates 2x and 2x. So what I can now effectively do is work out the heights of our triangle in terms of our coordinate system. So from this point to this point is our length p, our x value p, and from this point, the base of this triangle to the apex, is distance q. Okay, and we can now label the distances from our coordinate system for each of my triangles. So this triangle here, I can label that as 2x subtract q. That's my height of this triangle, and this length here is going to be 2x subtract p. So we've now got a coordinate system based upon several unknowns: the width of our square and height of our square, and also the coordinates of our apex of our common apex of our triangles P and Q. So there's our starting point. So we now need to put some numbers on, just so that we can start sort of setting up some equations. So we know that the blue quadrilateral area is a total of 32 centimeters squared. We know that the green one, we're told, is 20 centimeters squared, and we know that the little orange one is 16 centimeters squared, and this is the area we're after, and I'll just call that A. Okay, so we can start setting up some simultaneous equations based upon those values. So if we just start with the bottom left quadrilateral, we can see it's made up of two triangles, one with height Q and one with height, or if you prefer, width P, and the sum of those two triangles will give us the 16 centimeters squared. So I can say that x times Q divided by 2 plus x times P, because they have a common base area, divided by 2 is equal to 16, or I can say that x brackets P plus Q is equal to 32. So I can immediately get a relationship between x and my two coordinate points P and Q of my collective vertices 32 over p plus q. So that is one equation, unfortunately, with three unknowns. But we do have a means to, so I'll tick that one off, to create some more equations. And the beauty of this is if I create three equations, I'm going to have three unknowns, three equations, so I should be able to solve them. So I'm now going to deal with the green quadrilateral, which is made up of, again, two triangles, one with height 2x minus q, and the other with the height p. So again, we have xp upon 2 plus x, which is the base of the other triangle, 2x minus q over 2, and that is equal to 20. Okay, so we can now say that x p plus x brackets 2x minus q equals, multiply both sides by by 2, we get 40, and I'm going to leave that as it is for now, and I'm going to call that equation 2. Okay, and then finally we're going to deal with the big purple quadrilateral. So in this case we have a height 2x minus q of one triangle and a height 2x minus p of the other triangle. So this is going to be a little bit more complex. So we'll deal with this triangle here, which is going to be 2x minus p is its height with a base of x, and of course being a triangle divided by 2, plus, and then I'm going to deal with the second triangle here, which is going to be x brackets 2x minus q, its height, divided by 2, and we know that that's 32, or again multiply throughout by 2, and I end up with x 2x minus p plus x 2x minus q, and that must equal 64. So there's our third equation. So we've created from that diagram and our coordinate system three simultaneous equations, which I'll go ahead and solve.
So just a reminder, we've got our three equations. Equation 1 is x equals 32 over p plus q, and equations 2 and 3 have quite a lot of three terms in. So we're going to sub 1 into both 2 and 3 to eliminate x from both 2 and 3 and give us two simultaneous equations in p and q, which is what we're after. It's going to get messy, but let's just crack on with it. Okay, so 1 into 2 first. Okay, so everything in terms of x becomes 32 over p plus q, so that becomes 32p over p plus q, plus x on the outside becomes 32 over p plus q, and then inside we end up with two lots of x, which is 64 over p plus q minus q equals 40. Okay, so now we're going to divide through each term by common factor, which is 8. So that becomes 4, 4, and 5, simplifying things a little bit. And then we're going to expand our square brackets. So we end up with 4p over p plus q plus 4 times 64 is 256 over p plus q all squared minus 4q over p plus q, and all that we know is equal to 5. We can get rid of our denominators. I'm not a huge fan of denominators when solving equations, so we'll multiply throughout by p plus q squared, so we end up with 4p plus 2, whoops, sorry, 4p brackets p plus q, of course we multiply by p plus q squared, plus 256 minus 4q brackets p plus q, and that is all equal to 5 brackets p plus q all squared. Okay, it's not looking particularly pleasant, but if you notice, we have two terms here with a common factor 4 lots of p plus q. So what we can do is take that out, and we're left with p minus q, and plus 256 equals 5 lots of p plus q all squared. So what we can now do is subtract 256 from both sides. What I'm going to basically achieve with this is I effectively want to get a relationship between p minus q and some other terms. So here we end up with p minus q is going to be equal to 5 lots of p plus q all squared minus 256, and then divide through by 4 lots of p plus q. So we've generated a fourth equation, which will help us actually solve for p and q when we sub our equation 1 into equation 3 shortly. So now we're going to sub x into equation 3. So 1 into 3, just to generate another relationship and see where we go. So wherever we see x, we're going to be replacing it with 32 over p plus q as before. So this becomes 32 over p plus q, lots of 2x, which is 64, 64 over p plus q minus q, plus, you can see this is going to get slightly bigger than the other one, 32 over p plus q times 2x, which is again 64 over p plus q minus p equals 64. Just about squeeze that on. So you'll notice conveniently we have a common factor of 32, and then we're going to multiply, so that becomes 1, that just becomes 1. We're going to multiply everything out in our square brackets, so we end up with 64 over p plus q all squared minus q over p plus q plus 64 over p plus q all squared minus, oh word, this is getting unpleasant, p over, oops, remember that was 2, over p plus q equals 2. Okay, so as before, we can see there's denominators we like to eliminate, so we're going to multiply throughout by p plus q squared. I end up with 64. These two terms actually we can collect together, making the thing shrink down. So we end up with 128 over p plus q squared. If I multiply through by p plus q squared, I get 128 minus q brackets p plus q minus p brackets p plus q equals 2 lots of p plus q squared. That's actually much nicer to look at. And again, we've got a common factor of p plus q here, so we end up with 128. So we're going to take out minus brackets p plus q, there's our common factor, and then inside we end up with q plus p in this case, because obviously this negative will multiply through and give this negative p as we've got up there, which is equal to 2 brackets p plus q all squared. So we can now see here we've got p plus q and q plus p, same thing. So this thing here becomes 128 minus p plus q all squared equals 2, oh sorry, minus 2 lots. No, I was right the first time. P plus q all squared. You can see how easy mistakes are made. So I now know, if I take this term on the right hand side, that p plus q all squared, okay, there's going to be 3 of them on that side, is going to be actually equal to 128 over 3. If I take the square root of both sides of that, I get p plus q is equal to root 128, which is root 64 root 2, which becomes equal to 8 root 2 over root 3, and then I can multiply top and bottom by root 3. So I get a really nice relationship between p plus q and a surd, which becomes 8 root 6 over 3. Okay, so we've actually now finally got a numerical value for our unknowns P and Q. Well, we're nearly home and dry, I think. So we're going to plug our, I'm going to call this equation 1, P plus Q is actually numerically equal to 8 root 6 over 3. And we have a relationship between P minus Q in terms of P plus Q, which is convenient. So I'm going to plug all of this into here. So I end up with P minus Q, so obviously I'm doing 1 into 2 here, is equal to 5 lots of 8 root 6 over 3 all squared minus 256 all over 4 lots of 8 root 6 over 3, which looks pretty unpleasant as a fraction, but we can kind of tidy it up a little bit. So let's see what we can do with this. I can make my life complicated or not. What I can do is I can square 3 and bring it outside, so I end up with 5 over 9, and then I'm going to square 8, which is 64, square root 6, which is 6. Okay, and I'm going to subtract 256, and I'm going to divide all of that by 4 lots of 8 root 6 over 3, which is going to be 32 lots of root 6 over 3. So again, we've got fractions over fractions. What you'll notice here is we have a 9 and a 6, so we can divide through by 3, 2 and a 3, which is actually going to make my life a lot easier because I can now multiply top and bottom by 3. So I end up with 5, so the 3 underneath cancels. 5 times 64 times 2 minus 256 multiplied by 3 all over 32 root 6. So looking at that, I've got a common factor in 3 of the terms. 32 goes into 64 twice, and 32 goes into 256. 32, 64, 1, 2, 8 is 4 times, so that's 8 times. 8 lots of 32 is 256. Suddenly we've got something much more pleasant to look at. So we've got P minus Q equals 5 multiplied by 4, which is 20. Subtract 8 multiplied by 3, which is 24, all over root 6, which is unpleasantly negative, but we get negative 4 over root 6, which is equal to negative 4 root 6 over 6, which is equal to negative 2 root 6 over 3. Okay, not too keen on the fact that it's negative, so I can actually just swap our relationship round, so I end up with Q minus P equals 2 root 6 over 3. Okay, so we're gradually plugging away at this. Okay, so we're nearly home and dry. We've got our through relationships between P and Q and X, so we can combine our first 2 equations, just simply add them. So 1 plus 2 will eliminate our P's, so we end up with 2Q equals 10 root 6 over 3, so Q is equal to 5 root 6 over 3. Remember, that's our y value, our y-intercept on our coordinate system, our y value on our coordinate system of the common vertex of our quadrilaterals. And from this, we can sub Q back into the first one or the second one. It doesn't matter, but I know if I add P and Q, I get 8 root 6. So P clearly 8 root 6 over 3. So P is obviously 3 root 6 over 3, which is just root 6. So these are our x and y coordinates of P. Okay, so that was our point where the 4 vertices met of our quadrilaterals. Now we can then use our third equation, so equation 3, to get x equals 32 over p plus q, and p plus q comes from equation 1. So I'm dividing through by 8 root 6 over 3, which is identical to multiplying, excuse me a second, 32 over 1 by 3 over 8 root 6. Nicely, the 8 and the 32 cancel, so it becomes 4. So on the top we get 12 over root 6, and we rationalise that, which becomes 12 root 6 over 6, which is equal to 2 root 6. So if you remember, x was our base length, or 2x was our base length of our square, so we now know that our square had base length 2 lots 2 root 6, which is 4 root 6. Okay, so that was tough. And it went wrong a few times, but keep your head straight and you get there.
Okay, so that was brute force algebra. A lot of three simultaneous equations, a lot of possibilities to go wrong. In fact, it went wrong twice, making some basic errors somewhere within my calculations. I had to sift through it all and finally come up with the correct solution. But if this was a math exam, for example, one of the long questions, or if it was a UKMT senior challenge question, I would have wasted a lot of time and probably not ended up with the marks that I could have got using a more elegant solution. So the elegant solution is actually spotting that there are triangles of the same area. So, for example, if I look at the bottom left quadrilateral of 16 centimeters squared, and it's made up of a triangle of x base, another triangle with a base of x. Okay, now this height, I'm going to call this h1. Okay, I'm going to call this height h2. You'll notice that actually this height h1 is common to this pink triangle, so I'm going to call that a1 as well as this one. And then this triangle here, I'm going to call area a2, which has the common height and base of this one, same area a2. And as we move around clockwise, this one's area A3, which is the same as this purple one, A3. And then this is area A4. So this, I'll put my heights in. This is H3 and this is H4, just so you can see that they share the common height and they both have base area X. So there we have all the areas labelled A1 to A4. And the area we're looking for, A, is actually the sum of A1 plus A4. Now you'll notice that actually we can get that sum by adding these two, okay, which I know is 16 add 32, which gives us 48, and we know that 48 is going to be equal to A1 plus A4, which are these two triangles, but also plus A2 plus A3. Okay. Now, we obviously don't want that in our sum because it actually takes us over the area A1 plus A4 after, but conveniently we can actually get the area A2 plus A3 because in fact it's this quadrilateral here. So I know that A2 plus A3 is actually equal to 20. Okay, so I can sub that into here, and therefore, very straightforward with no algebra really required. I get A1 plus A4 plus 20 is going to be the area we're looking for, which is our area A, the missing piece. Okay, so A is going to be equal to 48, subtract 20, so the area is in fact equal to 28 centimeters squared, as we found before, but with a whole lot less work. And actually we can backtrack using the relationships that we use for our simultaneous equations and work out our values of p and q and also the value of x. Okay, but this was far easier and required a lot less intense algebra, and therefore I didn't make a single mistake. As you can see, I've now got my square with my 4 internal quadrilaterals on a grid, and I have the luxury of being able to expand my and contract my base length of my square and hence the height, so it scales up accordingly. And I also have a point which is the common vertex of the 4 quadrilaterals, which I can also move around. I'm going to call that point P on our coordinate grid, where the x coordinate was P, the y coordinate was Q. So we've now calculated, or previously calculated those values. Unfortunately, they were in third form, and unfortunately this works in decimals. We can do close approximations. So I know that this is 2x for the width of the square, which was 2 lots of 2 root 6, which is 4 root 6, which to 1 decimal place, I'm just going to drag it over to 9.8 or thereabouts. Okay, oops, it's quite difficult to get this right. And I also know that my PQ coordinates I can calculate. I'm going to put them in here and actually use the calculation function. So I know that P was equal to the square root of 6, which is not going to give me an exact value. It's going to round it to 2 decimal places. And I also know that Q was equal to 5 over 3 times the square root of 6. Okay, and close my parentheses, and hopefully that will be roughly the correct position to 2 decimal places. And if I click on areas, I should see 20, I should see 32, I should see 16, and I should see 28. Okay, so we are very, very close to the values that we calculated, or rather the 28 that we calculated, but of course this is suffering from rounding errors, so I think we did pretty well.